This is lecture 6 of Machine Learning and Bayesian Inference. In the last lecture, my main aim was to introduce the kernel trick. The kernel trick is useful because it allows you, by way of mapping your data into a typically bigger dimensional space than the one that you start with, you can then try and base a machine learning method on a fundamentally linear regressor or classifier. This is an important concept. On the basis of that, I then spoke about how you can take a somewhat more sophisticated approach to deriving the maximum likelihood or the maximum a posteriori training algorithms than using just straight gradient descent. Because in the regression case, you can then derive the training algorithm in closed form, at least assuming that what you want to be doing is still minimizing the sum of the squared errors. And in the case of classification, you can use a nicer approach, and you get from it the iterative recursive least squares algorithm, which is still a recurrence, but one that tends to converge much quicker than you'd expect with just straight gradient descent. So we're still firmly in the realms of things that are fundamentally linear, but we're now applying this kernel trick in order to make them more useful, in the sense that, for example, in the instance of classification, you can separate classes that wouldn't be linearly separable. Now, I'm going to reorder the lectures slightly, and I'm going to skip over what I was going to talk about, which was Gaussian processes, because I think if I do that and go straight now to support vector machines, things kind of progress a little bit more naturally. So I'm jumping forward to slide 110, and I'm going to keep developing this idea of using the kernel trick along with a linear classifier in order to develop, eventually, the support vector machine. So, what do we want to do? Well, we start this with a very simple and really quite compelling idea. And it's as follows. Instead of going to the lengths of setting up this big probabilistic framework, why don't we just bite the bullet and say, okay, if we have two classes illustrated here with the standard, kind of bog standard illustrative example for two classes, and we want to divide them with a linear classifier, why don't we just try and do that in such a way that the dividing line we use is as far away from any of these data points as possible, while still dividing them correctly? This is called the maximum margin classifier, and this is a very different approach to learning than any of the ones that I've spoken about so far. It's just saying, okay, we have feature vectors, we're going to look at two-class classification, let's just divide them in such a way that we keep as far away from any of them as possible. In some sense, this makes an awful lot of sense. Why would you draw the line between them so that it was close to any of the examples you have? The idea is to divide them, so you might as well try and divide them in what, intuitively speaking, looks like a very effective way. This is called the maximum margin classifier, for reasons that are hopefully obvious. Gamma is the margin, and it is the distance between your decision boundary, this straight line here, because it's a linear classifier, and the nearest of your training examples. And that will clearly be of equal distance from one class and the other class, as you can see illustrated here. That's quite a nice idea. I think it's quite a nice idea. We haven't, of course, yet bitten the bullet of what happens if, even in your extended, your higher dimensional space, after you apply the kernel trick, you still can't divide the classes linearly. Okay, I haven't spoken about that in detail, but all things will become clear. I'm going to talk about that as we go along. But this is the fundamental idea. We use the kernel trick, and then we try and use the maximum margin classifier. as a result of that, some very, very interesting things happen. The ramifications of this simple idea are really quite extensive. Now, in order to actually talk about how we might set this up in a way that allows us to find a learning algorithm to find that maximum margin decision boundary, that maximum margin classifier, we do again have to appeal to this simple geometry that linear classifiers have. Okay, so I sketched this in the last lecture, but now you have it all nicely typeset, and all the details are included on the slide. But it bears repeating. We have a linear classifier. F of x is W transpose x plus B. Now, here I'm going to call B the bias because we treat it separately. It's usually called the bias, of course, but what I really mean is I'm not necessarily going to call it W0. It may appear as either, but on this slide, it's to make it clear that it kind of has a distinct role to play. As I summarized in the last lecture, if you plot the solution of f of x equals 0, you get the dotted line that's on this graph. Okay, here we have the solution for f of x equals 0. And that is our decision boundary. The decision boundary then has a specific relationship to the weights in the vector W and the bias. The weights, as you can see here, are in a vector that is perpendicular to that decision boundary. The distance of the decision boundary from the origin then depends both on the size of the bias and the length of the weight vector. And what I didn't point out in the last lecture, but which is going to be equally important for the purposes of where we're going now, is that if you have some arbitrary point, then its distance from the decision boundary depends on the size of f when you plug that point into it, and the length of the weight vector. And this gives us a bunch of fundamental quantities that we need. Okay, it tells us how the orientation of the decision boundary, the straight line, the solution to f of x equals 0, is oriented, because it's perpendicular to the weight vector, and its distance depends on both the length of the weight vector and the size of the bias. And it also tells us how far away an arbitrary vector, x prime in this case, then is from that decision boundary. And that depends on the size of f of x when we plug that specific vector in, and on the size of the weight vector. And the final thing is that on one side of that decision boundary, f of x will have a value that is positive, and on the other side it will have a value that is negative. If you understand this little bit of geometry, then everything that follows will hopefully make good sense. So, what we want to know is, if we have some training data for a two-class classification problem, can we come up with an algorithm that finds that maximum margin classifier? The other question is, what happens if, even when we go into the extended space, the data isn't linearly separable? Well, we're going to look at both of these things. Now, this really is a fundamentally sort of non-probabilistic, non-Bayesian approach in many ways, but that doesn't mean that it's no good. It's, as I've mentioned a couple of times now, it's pretty much a gold standard learning algorithm, the support vector machine, for situations where you don't have huge quantities of data. And I'm suggesting here that you should read this paper, Do We Need Hundreds of Classifiers to Solve Real-World Classification Problems?, which is a big experimental study from 2014 in the Journal of Machine Learning Research. And you can download that for free because Journal of Machine Learning Research publishes stuff for free. Now, how are we going to go about this? Well, this ends up needing constrained optimization in order to derive a learning algorithm. I'm hoping that, again, you'll be able to go back to your NST Maths notes and remind yourself of how constrained optimization works to the extent that you've already seen it, because I think I do need to introduce some new things now. You are clearly familiar with maximizing and minimizing a function f of x without constraints. Okay, you know how to do this. You take its partial derivative, you set to 0, you try to solve the equations. I'm hoping that in NST Maths you will have seen something about how you might minimize, okay, or maximize. It doesn't matter, all right? Minimizing f of x is maximizing minus f of x. It's a trivial difference, so let's just talk about minimizing. I'm hoping you'll have seen something about how to do that with the constraint, typically that some function of x is naught. Okay, I'll illustrate what exactly this looks like in a moment. But what you probably won't have seen is how to minimize a function f of x with respect to both equality and inequality constraints. So I think that's where things are going to be new for you. So ultimately, what we want to be able to do is solve problems of the form in the box here. I want to find the value of x, which I'll call x opt, that minimizes f of x. Okay, it's argmin over x of f of x. And we are going to try and do that, or we're going to need to be able to do that, under a bunch of equality constraints and a bunch of inequality constraints. Okay, now that's going to be something that we need to use. Luckily, there are many numerical libraries that will do this for you, and there are also numerical approaches to doing this which are particularly good within the context of support vector machines. Okay, I am mainly going to concentrate on showing you how the problem of deriving the learning algorithm ends up being a problem that takes this form. I'm not going to speak again, as with some previous subjects, I'm not going to speak in detail about how you then address the numerical analysis. Okay, but there are libraries for doing this kind of stuff, and the important thing that I want to convey is how do you take the idea of a maximum margin classifier and cast it in an optimization form that has this format. Now, I suspect that this is the kind of constrained optimization that you may already have seen. And I think, once again, go back, look at the NST notes, and remind yourself of how this kind of thing works. What I have here is a simple constrained optimization problem in two variables with a single equality constraint. The left-hand graph here is a contour plot of this function that we want to minimize. Well, actually, we want to maximize it in this case. Well, there's a correction for the slides next year. Sorry about that. So the contours for f of x, y are on the left here, and rather than finding a global maximum for f of x and y over the whole of the xy plane, we're now introducing an inequality constraint. Okay, that's actually linear. Okay, we want to maximize it, but only along the line described by g of x and y. Now the value of fxy along that line is shown on the right. Okay, hopefully you can relate that to the contour plot on the left, where the dotted line corresponds to g of x, y equals 0. Now in this case you might be able to get somewhere by turning this essentially into an equation only in x and then solving and then carrying that through to get a value for y. But there is a general method that's much more generally amenable for solving this kind of constrained optimization problem, and that is the method of Lagrange multipliers. So I'm hoping that that terminology is something that that is at least a little familiar to you, and that you feel now that you've actually heard before. The method of Lagrange multipliers says that if you want to solve this kind of problem, you form a Lagrangian, which is the thing you're trying to optimize, minus lambda, which is called the Lagrange multiplier, times the function that describes your equality constraint. And we know then that necessary conditions for the solution are as given in the box here. You want to be able to set the derivative with respect to each variable, with respect to x and with respect to y, to 0. And that then gives you the equations that we see here, one from each of the equations in the box, and one which just follows on directly from the constraint, okay, which is this one. And if you solve those equations for x and y and the Lagrange multiplier, you will find that the solution comes out quite nicely. Okay, so that's just an illustration in 2 dimensions. It works perfectly fine in multiple dimensions. And perhaps more importantly for our purposes, it also works if you have multiple constraints, not just the gxy equals 0, but g1xy equals 0, g2xy equals 0, and so on. You just introduce a separate Lagrange multiplier for each of those constraints. So we're going to want to go a little step further than that. Okay, in the problem that we're going to need to solve, we actually need inequality constraints as well, and I've written that in its kind of a more general form here. We want to find the x that minimizes f of x, subject to, in this case, n equality constraints as before, but also m inequality constraints, which differ only in the fact that instead of having a function of our variables be equal to 0, we now want it to be greater than or equal to 0. So in a sense it's a slightly softer constraint that we would introduce when we talk about an inequality constraint as well. But the Lagrangian part of solving this problem isn't really any different. Okay. Now, in order to address one of these problems, we form a Lagrangian that's a function of the x we're optimizing over, and lambda, which is a collection of Lagrange multipliers for the equality constraints, exactly as before, and alpha, which is a collection of Lagrange multipliers for the inequality constraints. Other than that, the Lagrangian is formed in the same way. The difference now is that the necessary conditions for a solution are moderately more involved. These are called the Kuhn-Tucker conditions, and they actually end up telling us something quite important about the solution in the case of support vector machines. What they say is this: we're now going to require that when x prime is a solution, there are values for the Lagrange multipliers such that, once again, the derivative of the Lagrangian with respect to the x vector is 0. That's unchanged. The constraints will be satisfied at x prime. Okay, well, that's certainly necessary. But then the necessary conditions require that the Lagrange multipliers for the inequality constraints are non-negative. That's condition 3. And we also have this condition 4, which is slightly more involved, but which I'll come back to later, because that tells us something useful. Okay, the take-home message from this slide, though, is that this extends to the case with inequality constraints, and the necessary conditions for the solution are just slightly more numerous. Unfortunately, as is often the case, the time constraints for this course mean that I don't have time really to go off on a bit of a numerical analysis tangent here and talk about how you might write code that actually goes about solving these kinds of constrained optimization problems. So this slide is really just a little bit of a taster for if you do want to get involved in that kind of stuff. What I've just described is called the primal problem for this kind of constrained optimization. There is also a dual problem, which I've stated here. Sometimes working with the dual problem is easier than working with the primal problem, but I emphasize I don't have time to get into the real numerical analysis. If you want to, then there's a good book, Numerical Optimization, that I've noted at the end of this slide. Okay. I still need to talk about the conditions for the solution for the optimization problem, because once again I emphasize they tell us useful things about what the support vector machine solution actually ends up looking like. So we want to put this idea of the kernel trick into the context of a maximum margin training algorithm. We want to do it again in the extended space. So the actual underlying linear model that we use is essentially exactly the same as we've seen in the last lecture. F of x here, depending on the weight vector w and the bias weight w0, is just a linear function within the extended space, because x is being mapped into that extended space now by capital phi, which is exactly as defined in the previous lecture. Having done that, we know from the geometry that f will be positive on one side of the decision boundary and negative on the other side. We just use whether it's positive or negative to denote the classification that's associated with it then. Okay, so the activation function now, because we're kind of outside of the probabilistic context for a while, is just a hard step function that gives us +1 denoting the first class or -1 denoting the second class. It's no longer the smoothed off sigmoid, but it essentially plays the same role. Now, the reason that I'm using +1, -1 rather than +1 and 0 to denote the two classes is just that it's notationally more convenient for talking about support vector machines. And for a similar reason, I'm keeping the bias weight W0 separate from the rest of the weight vector rather than just rolling them all into one, as I did earlier, because it's notationally more convenient now. We want to be able to derive an algorithm in the form of a constrained optimization for finding this maximum margin solution now. So the step one is just to consider what's happening now that we map into the extended space. And the answer is, well, it's not much different. Okay, we've just mapped using capital phi into an extended space. We're going to classify using the sign of this function. Okay, class +1 if f of x is bigger than 0, and class -1 if f of x is less than 0. And in the extended space, the geometry remains the same as previously. Any point x prime will now be mapped into the extended space as phi of x prime. And everything else stays the same. Okay, now the margin, which I'm calling gamma, which is the distance from phi of x prime to the decision boundary, given the weights and the bias, just has this value here, and the orientation of the decision boundary is exactly as it was previously. So there's nothing new there. Let's just take this a step further. We have a bunch of training examples, which are pairs x sub I, y sub I. The label y will now be plus or minus 1. And the reason for using plus or minus 1 hopefully now becomes clear. If f, when we plug the ith training vector xi in, gives a positive number, and the label yi associated with xi is plus 1, then this product will be positive. Okay? Whenever f is classifying the ith training vector correctly, that quantity will be positive. Okay? Similarly, if f classifies the ith training vector incorrectly, in that it gives a positive output when yi is negative, minus 1, or it gives a negative output when yi is plus 1, then the product will be negative. Okay, so this quantity would be positive precisely when f is predicting the ith training example correctly. And so having set up that little piece of notational trickery, what we have in the box here is one way of formulating the idea of the maximum margin classifier. Okay, we are trying to maximize over settings of the weights and the bias. What's in the brackets here? Okay, well, this is the important quantity geometrically. Okay, so for each training example, the quantity that I've just circled to essentially corresponds to this part here. Okay, on the graph, it's mod f of x prime. On the equation, it's yi times f of xi. Okay, so dividing that by the length of the weight vector, I'm just referring to here again, that is going to be large when the margin gamma for the ith training example is large. Okay, and that training example is being classified correctly. Because yi f of xi is positive when f is giving a correct classification for the ith training example, dividing by mod w then gives us the distance of the ith example from the decision boundary, and we want to maximize the smallest of those. Okay, the minimum with respect to I here is telling us how close the closest training example is to the decision boundary, and we're trying to maximize that distance. Okay, if you look back to the earlier slide, we are trying to maximize the smallest distance gamma, okay, over the whole training set, and that's exactly what's just been written down. Okay, so that's one way of formulating it, and it is completely and utterly horrible, so we won't say much more about it. Okay, it's completely horrible because essentially it has this horrible discontinuity in it. We are having to take a minimum over this finite collection of training examples, and then when trying to do a maximization problem, in a kind of continuous way with respect to that. So this is the obvious way of formulating the problem, but unfortunately, for any practical purposes, it's a bit of a non-starter. So we need to look at this in a slightly more subtle manner. Okay. There are two ways in which you can reformulate this in a nicer way, so that it turns out to be a constrained optimization problem. The first thing you need to note is that you can apply a constant factor to f arbitrarily without changing the position of the decision boundary. Because the decision boundary is where f of x equals 0. That's defined by this equation here. And if I multiply through by an arbitrary constant c, nothing changes. Okay? But we do, of course, then scale both the bias weight and the weight vector w. And we can do that in any way we like. So that means that we can actually fix the mod of the weight vector w to be some specified value. Or in fact, we set mod w squared, okay, because that way we avoid having to take a square root that's involved in computing the modulus. Now, the advantage of that may require a little bit of thought. It's geometrically fairly straightforward, but you may have to just mull this over a little bit to really get your head around it. If we fix the value of mod w to be 1, then the distance from the origin of the decision boundary is just the size of the bias weight. That gets simplified. The distance of an arbitrary point capital Phi of x prime in the extended space is just the value of f of x prime. And that gives us the margin. And we can formulate the learning problem as in version 1 in this box here. Okay. We can try and maximize the value of gamma, which is a distance between the decision boundary and some training point, subject to the constraints that our weight vector has a length of 1, and this quantity is at least gamma for every training example. Okay? Like I say, you may have to think about that a little. I hope it is, however, clear that this achieves what we're trying to achieve. Okay? The main thing to remember, once again, is that this quantity, for the ith training example, is positive if f is putting that example on the correct side of the decision boundary. The second point is that because we've imposed the constraint that the mod of w is 1, this quantity, if f is putting the ith example on the correct side of the decision boundary, is actually this distance. Okay? So what we're saying is, make that distance as big as you possibly can under this constraint, because that corresponds precisely to how far away the closest training example will be from the decision boundary while keeping them on the correct side. Okay, so that's one way in which you can formulate this. Now, there's a second way, and both of these will work. The second way is to say, well, instead of constraining the modulus of W, you can essentially kind of define distance however you want and allow this quantity to be represented by anything you like. Okay, you can essentially redefine the distance of the closest example to the decision boundary to be 1 at the solution that you're looking for, and then fit to that by controlling the modulus of W. Okay, and that way you get a similar constrained optimization formulation, where we say, once again, this quantity will be positive whenever f puts the ith example on the correct side of the decision boundary. Depending on the modulus of W, there will be some actual distance there, but we've just decided that we're going to have a distance of 1 and adjust mod W to take account of that. So now we're still introducing a margin, which is saying that the closest example should be a distance of 1 away, and we're going to optimize in order to minimize this quantity here. Now, the final thing to note in this version of the formulation is that by minimizing the mod of W, we are, of course, maximizing this distance. Okay, so we're still maximizing the margin. Both of these formulations of the maximum margin problem are in the format of a constrained optimization problem with equality and or inequality constraints. If we look at version 1, we're maximizing a very simple function, just gamma, subject to a single equality constraint and m inequality constraints. In version 2, we're still optimizing what looks like a pretty straightforward function, just the length of W. And now it's subject to just m inequality constraints. That means we can now plug in the idea of the constrained optimization and turn the handle and see what happens. So I'll do that for the second formulation. If you do it for the first formulation, you'll basically find that you get the same conclusions. I've summarized here what the second formulation is. Okay, minimize essentially just the length of the weight vector such that for each of the training examples you get this inequality constraint, saying that it's on the right side of the decision boundary and it's a specified distance away at least. So we can write down the Lagrangian, which gives us this expression. Okay, it's just the function that we're optimizing, minus, now a sum with one element for each constraint, with a Lagrange multiplier, alpha, and the constraint that we're trying to impose. And the necessary condition for a solution first says that these partial derivatives with respect to the parameters that we're optimizing over, the weight vector and the bias weight W0, the conditions require that these partial derivatives are now 0. So let's differentiate this Lagrangian, equate to 0 and see what happens. What happens is this. Now, we're back in the realms of straightforward partial differentiation here, so hopefully I don't have to go through this in too much detail. I don't think there's anything controversial. It is differentiation using functions expressed in terms of vectors and matrices. So if you've done a bit of practice with that stuff now, this should be straightforward. Okay, the derivative with respect to w for the first term here just comes out as w. That's nice. Then mostly the derivative with respect to w of this part of the expression disappears. We just need to differentiate what is in fact f. Okay, and that's already been done several times in the preceding work. So the derivative looks like that, and we're going to equate that to 0 in a moment. Similarly, for the derivative with respect to the bias weight, in this case we end up with this expression here. Okay, so follow these through step by step. They shouldn't give you too much of a problem. Now, what does this tell us? Well, if we equate those to 0, which is the first part of the necessary conditions, and if we look at the Krushkin and Tucker conditions, we now learn several things. The first is that the weight vector has this very specific form. It can be written in terms of, essentially, the training data. Okay? It is a linear combination with weights corresponding to the Lagrange multipliers, which are the alpha I. Okay, now this is going to turn out to be important. This equation has ramifications, so I'm going to make an issue of directing your attention to it. We're going to need it in a little while to show something pretty significant. Okay, but that's the first thing. W can be expressed as this sum, essentially just using the training data. Okay, the extended versions of the xi's, the labels yi, and then these weights which are given by the Lagrange multipliers. The second thing we get is this constraint, which I'm not going to say any more about because I don't really, as I said, want to get into what you need to do with the dual Lagrangian. And the third constraint we get out is this. Okay, the third requirement is this. So what's going on here? Well, that third requirement is in itself quite nice. We have to just think about what it says. Okay, it says that either alpha I, the ith Lagrange multiplier, is 0, or this expression is 1. Okay, which makes the contents of this square bracket here 0. One or the other of those must be the case. Okay, for each I, okay, for each training example. And what that tells us is that the training examples, when we have a solution to this problem, will fall into two groups. The ones for which yi fxi is 1. Now, we were constraining the solution with that value being at least 1. Which means that the examples for which this is the case are the ones that are closest to the decision boundary. If we go back and look at the initial kind of intuitive way of formulating the problem, they are the ones that are closest to the decision boundary. They are these guys. And unsurprisingly, the other group are the examples that aren't the closest ones possible to the decision boundary. Okay, so the ones for which this is the case, okay, for which yi f of xi is not equal to 1, and which therefore have a corresponding Lagrange multiplier, alpha equals 0, these are the ones that are not the closest examples to the decision boundary. Now, why might that be nice? Well, okay, let me just give you the diagrammatic summary first, just to fix this in your heads. The circle examples are the vectors with positive non-zero Lagrange multipliers alpha, and those are the closest ones to the decision boundary, and the other examples are the ones with zero Lagrange multiplier. Well, that tells you a couple of things. Firstly, it's probably intuitively safe to assume that most of the training examples will be in the group that aren't as close as possible to the decision boundary and will therefore have a zero Lagrange multiplier. That means that this expression that we derived for the structure of the weight vector is going to have a lot of zero elements in its sum, because you'd expect only a small number of those training examples to be as close as possible to the decision boundary, and those are the only ones for which the ith alpha will be non-zero. What we can also say is that because of this expression, you can kind of think of the elements in alpha, the Lagrange multipliers, as being an alternative set of weights that you're choosing as a result of running the training algorithm. Okay? What we've said is that if you cast the training algorithm as a constrained optimization problem, it will give you W in this form, but the yi's and the xi's are fixed. These are training data, and so we can regard the alphas as an alternative collection of weights that's output by the training algorithm. Now, if we do this, we get something interesting. What I've done in the second half of the slide here is written what the classifier is going to be after we train. Okay, say we've chosen W0 and W by solving this constrained optimization. I've then taken this expression for the form of the weight vector and I've plugged it in here, which gives me the second line. Okay? And that results in me having an inner product. Okay? An inner product between one of the training examples, the ith training example, and x, which is any new vector that comes along that I want to classify after I've done the training. And the classifier, once trained, then can compute its output just by taking inner products in the extended space between the new thing that it's trying to classify and each of the training examples. Now, this inner product is called a kernel. See, I promised you I'd tell you where the kernel in the Kernel Trick comes from. But I emphasize again, this way of writing the classifier after you've trained, okay, after you've chosen W and W0 to solve this maximum margin problem, has to take on this form. Okay, it has to be something you can write in this way, and that's because the necessary conditions for solving this constrained optimization problem force the weight vector to be expressible as this sum. Now that has further ramifications. Just remember where we started. Okay. We started by introducing this big phi function to map things into a bigger space. Now that's turned out to be quite fundamental, because the entire structure of the maximum margin classifier ends up having quite a nice expression in terms of inner products within that space. And we can draw out a practical consequence of this fact. Let's say we're actually dealing with a hard classification problem. Okay, we're not just dealing with the toy data as I was previously. It's not just a couple of classes that split into two clumps each in such a way that you can't draw a line between them. Let's say that this is a real big, gnarly, nasty, applied two-class classification problem. In order to go into a higher dimensional space in such a way that we can solve it with the underlying linear model, we might expect that we actually need to go into quite a large number of new dimensions. Okay, what that means is that you would have lots of basis functions. So k is big. K is the dimension of the new space you're going into. Now, what consequences does that have in this case? Well, if you write the form of the classifier in its standard format, this inner product is then a sum with k terms in it. Okay? And we've just suggested that k may in fact be very, very large. That's not good. If k is sufficiently big that computing this sum becomes a problem. But what then happens if we write this in the alternative format by essentially treating the Lagrange multipliers, the alpha i's, as an alternative bunch of weights? Well, what we have now is a sum over m things, where m is the number of training examples. Okay? So we've potentially made that sum a lot smaller, and in fact we've potentially made it smaller even than we'd initially expect, because we've already noted that a lot of those alphas will be 0. Okay? Potentially this sum has fewer terms in it than the number of training examples, whereas this one has a number of terms in it that's equal to the number of dimensions we're mapping into. So hopefully we've actually made things a bit more efficient by going to this format. But you should be about to complain, because in order to compute this inner product, you're taking a sum of k terms. And here's where something rather wonderful happens. It turns out that there are kernel functions, k, which are very easy to compute, but which compute the values of inner products in very, very high dimensional spaces. And by that I include infinite dimensional spaces. Let's just step back and consider that for a moment. Let's say, going back to my original introduction of the kernel trick, you're taking your vectors x and you're mapping them into a space of higher dimension. We can conceive of mapping them into a space that is infinite dimensional. Okay? This works, and in fact the most commonly used kernel function that I'm about to introduce for support vector machines corresponds to an infinite dimensional space. Okay? Now there's something called Mercer's theorem, which I'm not going to talk about in detail, but it characterizes precisely when a kernel function k has a corresponding set of basis functions in such a way that k applied to two vectors gives you the value of the inner product that you would get if you'd mapped them into a bigger space using those basis functions and then taken the inner product. So this is a nice payoff. Okay? Once again, just to summarize, let's say we have an absolutely massive k, possibly infinite, then we have a very big sum here which we have to compute in order to classify a new thing x. If we exploit the structure that we know the solution vector w must have, when we train using the maximum margin, we change that sum into one that has only m things in it. That's the number of training examples. and we would expect it to have even fewer than that because a lot of the alphas will be 0. There's then the potential problem that we'd expect this inner product to require a sum of k elements, but Mercer's theorem tends to come to the rescue, and it can give us a function or a kernel k which can compute that inner product without having to evaluate a sum over all those k terms. So we end up with this version of the trained classifier that's written in terms of an underlying kernel. Now the question then, of course, should be what sort of function should you use as the kernel? Well, anything that Mercer's theorem tells you can use, but that's a big subject in itself. There is considerable work in the literature on designing kernels for support vector machines that are applicable to specific kinds of data. Having said that, you will tend to see two kinds of kernel used. The first is the polynomial kernel, which looks like this and has two parameters C and D, D being the particularly important one, which is related to the number of essentially product terms you use between elements of the x and x prime vectors. And the second one is the radial basis function kernel, and this really in practice is the one that is overwhelmingly the most popular. And this too has a parameter, in this case sigma squared, which, well, this should look fairly familiar. You know what shape this thing has. It's like a normal distribution, and the sigma squared affects the width. Now, those parameters, CD, sigma squared, are important. We'll come back to them later because it's important to set them correctly. But be aware that if you see a support vector machine used in practice, it will probably be applied using a radial basis function kernel. But that there are many, many others that are aimed at specific kinds of data. And as I hope you're beginning to infer now, it is the case that in practice you would probably want to try a bunch of different kernels and see which one works best for you. So in summary, because there's been quite a lot of content in the last 50 minutes or so, we can use the kernel trick, and then we can make an intuitive judgment that says that once we're in the bigger space, maybe we should choose a dividing line between the two classes that is situated as far as possible from the training examples we have, while having them on the correct side of the boundary. Okay, that's point one. Point two is that in order to implement that training algorithm, okay, choose the dividing line in that way, we can formulate the problem as a constrained optimization. Okay, that's point two. Point three is that the theory that's available that tells us about that kind of constrained optimization problem then tells us what form the solution has to take. Okay, the solution being the weight vector and the bias W0 that we get out. And it tells us that W in particular has a specific form. When we plug that form in and look at the format that the trained classifier has to take, we then find that it involves computing inner products between the training examples and the new thing that we're trying to classify. And it turns out that while that, for a high-dimensional space, might be tricky, Mercer's theorem provides us with kernels that can compute, in some cases, those inner products in a very straightforward manner. Okay, if you look at the radial basis function kernel, all you're doing is looking at the distance between a couple of things and taking an exponential. Okay, that's not tricky. So that's the maximum margin version. In the next lecture, I want to talk about turning this into a full-blown support vector machine by adding a couple of further things that allow you to deal with the case where you might, even in the larger extended space, not be able to separate things properly using a linear model.